Let me record this. Okay. So as you can see, this is the lab menu we have. I wish I can use that. I'm going to open. Yeah, it's better. It's much better. Okay. So I hope I hope you guys could see what we have right now. Okay. So this is the lab menu of the lab one, and everything in here you should already know. Okay, this is a pivot point, and this is a balance beam in here. This is a toroid shape. Okay, so I'm going to say a little bit about the pressure distribution in here. Let me see. Okay. As you can see, the toroid shape, the reason we designed the device like this is because in this picture, you will see the hydrostatic pressure is like this, okay? The distribution is like this on this vertical surface. The hydrostatic pressure distribution is like this. But what if in the inner curve and the outer curve in here, we still have the hydrostatic pressure? It's like that, right? The hydrostatic pressure is always normal to the surface, okay, and become bigger and bigger. I mean, I want to show it clear. It's like that, okay. The deeper the depth is, the pressure force is a little bit more, and the same with on here.
Excuse me?
Mm-hmm.
Right now, we still only see the lab manual. I see what you're drawing, but it's on the lab manual page. Unless,
Okay.
yeah, did you mean to change the picture or something?
Yeah, because I don't know if you can see the pressure distribution I'm drawing. No.
Yeah, we see the lab manual and the yellow marks you're making.
Yeah,
Okay.
it's just on the wording, so it's kind of hard.
Oh, really?
Well, we see the yellow stuff, but when you write, oh, you haven't written anything. Okay.
So actually, I'm drawing on the picture of the device. So.
No, we don't see any picture.
Oh, really?
Yeah, we see the lab manual. This is title page and
Oh.
table of contents, and yeah.
Okay. Yeah, my bad. Let me see. Okay. So can
Yeah,
you?
there it is.
Oh, okay. So
Yeah, we see it
I
now.
I know what's happened. I think I was sharing the lab menu on the Chrome, and not showing the lab menu on the Acrobat. So the screen is all the screen is still in the. Yeah, that's fine. I'm just redo it again. I think it's easier to understand, right? We have
Yes, much better.
yeah.
Thank you.
Yeah, you have a pressure in here, you have a pressure in here. Okay. And what we want to do is we want to find a sorry, not this one. We're trying to find a hydrostatic force, the resultant force in here. So I'm talking a little bit about the pressure force on the curved surface. So the reason why we designed the toroid like this is because, as you see, all the force are normal to the surface, right? And because it's normal to the surface, so if we extend the pressure, it will go to the pivot point, right? So if we are having like, let me see, if we have a moment balance, the pressure force, all the pressure force in here and in here doesn't make any contribution to the moment of the pivot. Okay, so for this pivot, we have a balance force. Let's see, this is our W. So, and the length in here is L. Okay, so this force will give in the pivot point a counterclockwise movement. Okay, W times L should be equal to the hydrostatic force only on this vertical surface in here. Okay, so that's why we only care about the force on this vertical surface, but not on the curved surface, because all the force are going to the pivot point, and in the moment balance, it doesn't has any contribution to the equation. So on the right of the equation, it will be F. Yes. Why? Someone is someone is drawing for me, right? Yes, the F. Okay, times the distance in here. Let's call it whatever, L1 or L2. L1. Okay. So as you know, we have the water elevation on the side, and we are able to get the numbers from the side, and the number we are recording is actually from the bottom of the toroid to the water surface. Okay, so that this distance is what we're recording. We call it Y. So if the water is 150, 160 is actually from the bottom of the toroid to the free surface. And it's actually not this distance. It's not L1 we're trying to calculate. So, but we're able to find the L1 easily using the trigonometry relationship. Okay, let me remove everything in here. Okay, let's to next page. Okay, as you guys can see, this is let's see, this is the equation of the theoretical center of pressure, and I think all of you may be very familiar with that because in homework 2 there's I think one or two questions are related to this one. So this equation, the y bar is from the the free surface to the centroid of your interest, the area of interest, and area is what is the area what you're going to calculate, and xc is the moment of inertia of the surface. So in our case, I mean, what will be, let me draw a picture in here. Okay. So if we have a shape like this, okay, and this is our water elevation. Okay. And this one I'm going to show is, okay. So if you see from this side, it will be look like this. Okay. And I'm telling you the height of this surface is 100 millimeter. And the width, I think the width should be given in the lab manual, probably later. I don't know. I can see it right now. I think it's a 50 or 30. I'm not sure. So in this equation, the y bar is from the top of the water, from the free surface to the center, to the midpoint of this area, okay, to here. That's our y bar. We're able to calculate. And IXC, I think you guys already know, is 1/12 B times H cubic. Okay. Let me see. And the B is a 50, H is a 100 millimeter, and the A is just a 50 times, the area is just a 50 times 100. Okay. And that gives you the theoretical YP. And we're going to use this theoretical YP to compare with our experimental YP in the next equation. Let me just remove. Okay, so you don't really have to pay attention to this part. It's all the derivation of the equation, and what you need to pay attention is when you calculate the area in here. When you calculate the area in here, you need to pay attention. Submerged part, the areas is only we're talking about the vertical surface, and if it's a fully submerged, we're using the area of the vertical surface. But if it's a partially submerged, we need to using this equation. Okay, it's the area will be A is equal to Y times B. And if it's a fully submerged, it's R1 minus R2 times B, which is mean this is the outer diameter. Oh, sorry, it's the outer radius of the toroid, and this is the inner. R2 is the inner radius of the toroid. So R1 minus R2 is the height of the vertical surface times B, which is the width. So that's the area of the of the vertical surface. But if it's a partially submerged, it basically means it's the width times the submerged height. Where we're able to calculate the A. So the A is different in two equations. Just pay attention to this. And we have the equation 1.2, 1.3, and it goes to 1.4. And 1.5 is what we're going to use for the calculation. And 1.3, the 1.3 in here, F times YP plus H equal to W times L is basically what I have already mentioned is a moment equilibrium. And using this relationship, we are able to calculate the YP using all the informations in here. So the M is how much gram of the weight on the side. So we have the M, we have the L. L is a given. It's later in the in the data, and rho, that's easy. Y, you're able to get it. A minus H. And let's see. You have a picture in here. So all the information you're able to get from this figure. Okay, so you're able to calculate another YP using the data. The H in here is related to the measurement because we take the measurement of the water depths, and using that one we are able to calculate the H Y bar. So Y bar and H are related to the number we report, and the M is the the mass Okay, it's a mess we record. So probably I will send you the data tonight. It will give everything in here. So you will have everything in here. You're able to calculate a experimental YP. Okay, that's pretty much the equation I need to mention because it's a relatively easier lab. The only thing we need to pay attention is equation 1.1 and equation 1.5. Okay, let's see. We have analysis of data. Okay, the first one is categorized fully submerged and partially submerged. It doesn't really matter. The second one is for each depth and mass setting, calculate the Y bar, YP theoretical, and YP experimental. Okay, so I think it's the Y bar is just from the free surface to the centroid, and YP theoretical and YP experimental I already explain how to calculate it in the equation. It's just equation 1.1 and 1.5. Create a table comparing YP theoretical and YP experimental as a function of Y, which means you have okay, let me just draw something. So for this one, as a function of Y, so which means the horizontal axis is Y, your Y, and your vertical axis is your F, F and theoretical. So it will be like this one. You have a several data point, and you have another several data point as the experimental. It won't be exactly the same. Okay, so what I want to see is like we have a two line, and we can compare it. I mean, it won't be like this. I think it will be a straight line or something. I don't remember, but the data set, the figure I'm trying to get is something like this. And plot F. Okay, F is so I think we're having the force. The force. What is the equation of the force? Okay, it's in here. So the force is equal to rho g y bar times a. It's easier. It's easy. So you're able to calculate it. And F experimental. Okay, so we have the force theoretical and the force experimental. Also, let me see. Which one? In this definition, what is the force in here? Theoretical force is in here, and the experimental force can be calculated. Okay. What is the due to the? Okay, this is our theoretical hydraulic force, and using the equation 1.3 in here, if we plug the theoretical YP into this equation, we're able to get the experimental F using the equation 1.3. I don't know if it's the information is given in here. Okay. Calculate the F experimental using equation 1.3 and 1.1. Okay. So yeah, that's it. Yeah, the equation is given. Okay. So we need to calculate the force theoretical and experimental, and the plot, just like what I showed before. So the rest of it is just the data analysis part, but everything in here you're able to calculate. So just to follow an instruction, and you guys are able to calculate everything. And discussion point is basically some conceptual question about this lab, and I hope you guys could able to answer this question using your own words. And if you have any question regarding the discussion point and the data analysis, you can let me know. My office hour is on Wednesday, Monday, Wednesday, 1 to 3 p.m. So you guys could join the same same room, and I think or just shoot me an email. I think I will answer all the questions you have regarding the lab and also the homework. So let me see what I left. Okay, so in the data table, as you can see in here, R1, R2, B. B is the width of the toroid. The L is from your weight to the pivot point. That's the length. And R1 is the outer radius of the toroid. R2 is the inner radius of the toroid. So that's basically all the information you need. And you can see the table in here. We measure one Y value. We have a value of a mass, corresponding value of mass, fully submerged or partially submerged. Yeah, I think you don't need to worry about that. So the data I'm sending you, I will tell you if it's a fully submerged or partially submerged, so you're able to look at the equation you need. So basically, it's two column of data, and that's pretty much it. Okay, that's pretty much all for today's lab. Thank you for watching. I think I'll record the most part, especially for the menu description, and later I will upload it to the Blackboard. So thank you guys for coming, and you have a wonderful night. Thank you.
Thank you.
Bye bye.
Thank you.
Bye.
Thanks, man.
Bye.
Thank you.